So I'm going to be doing a quick walkthrough of Lab 1 here, which was the left and right rotate simulation, which is a data-dependent rotate. So just going to quickly look at the code for left rotate here. We have our A input vector, standard logic vector, 32 bits. B, also 32-bit in this case because the lab stipulated that we should allow for rotations greater than 32 bits. And then O, of course, which is our output vector. Of course, in the architecture for our left rotate, we're only going to actually use the 5 least significant bits of B for our select statement, because essentially if we have more than 5 bits for a 32-bit rotate, we can just kind of ignore them and only take into account the 5 least significant, and the output will be the same. So yeah, standard data-dependent rotate based on what we had talked about in class. You're going to see very similar code for right rotate, of course. And then we have our test bench modules as well for each of them. So these are our test cases here. I've also outlined them in the document here as well. Let me quickly launch the simulation just to show how it's tested. So you have to zoom out to a point where it's actually useful. So we did a 10 nanosecond delay on each input. Yeah, so this is a little better. Scroll back to the beginning here. We have A up top, B in the middle, O at the bottom. So we have our A's, and then for each A we have 2 input B's that show different rotates. In this case, the output is only one line because I was showing that we can essentially ignore the bits greater than the 5 least significant, as I was saying, in the case that we are past something bigger, and we'll get the same rotation as long as the 5 least significant are the same. Yep, so anyway, we have another A, 2 more B's, and then it will repeat. But same deal for the other rotation as well. And then just quickly, just going to talk about this. So gate representation of the mux. I chose to do representation of the mux using AND gates and an OR gate. So these bits up here, S1 through S5, are the least significant bits of B that we pass in. If you were to do a truth table, you could work all this out, where you pass each of them into AND gates just based on the truth table. And then we would get our concatenation based on what our B was that was passed in. And essentially, with 32 gates here, only one of them is ever going to pass at one time to our output, which is an OR gate. And yeah, that's pretty much it. I apologize for the quality of this, but this is the best I could get for this image. So if you look at the code, it's in the same order, so hopefully it's clear. This is the left rotate. But yeah, anyway, thank you for watching.